Ever wondered how medieval villages survived droughts that lasted years while modern cities struggle with water shortages after weeks? Archaeological excavations reveal sophisticated rainwater harvesting systems that collected, stored, and distributed water to thousands of people using only gravity and clever engineering. These underground water cities could sustain entire communities indefinitely, ready to discover their genius. Part 1. The Water Crisis Drought Reality. Medieval communities faced water crises that would devastate modern cities within weeks. Historical records describe droughts lasting 3 to 7 years, where rivers dried completely and wells became poisoned or empty. Village chronicles from the 13th century detail communities watching their water sources disappear month by month, with families rationing single cups of water per person daily. Unlike today's interconnected water infrastructure, medieval villages were completely isolated during emergencies. No emergency deliveries, no backup systems, no government assistance. When the water ran out, people died or abandoned their homes forever. These weren't rare events, but regular survival challenges that occurred every decade, forcing communities to develop permanent solutions or face extinction. Failed solutions, traditional water sources proved unreliable during extended dry periods, leaving medieval communities desperate for alternatives. Wells that had served families for generations suddenly ran dry or produced contaminated water that caused deadly diseases. Rivers that once flowed year-round became seasonal streams, then disappeared entirely during drought cycles. Even successful welding projects often failed because groundwater levels dropped below reach of medieval excavation techniques. Spring-fed sources became unreliable as underground water tables shifted during climate changes. Purchasing water from distant sources was economically impossible for peasant communities already struggling with crop failures. Storage methods, using simple barrels and containers, couldn't hold enough water for extended droughts. Medieval communities realized that depending on traditional sources meant accepting periodic catastrophic water shortages that could destroy entire settlements. Crisis point. By the 12th century, recurring water crises forced medieval communities to innovate revolutionary solutions or face complete abandonment. Village records describe desperate measures, including drinking contaminated water that killed dozens, rationing water so severely that people couldn't cook food, and abandoning settlements that had existed for centuries. The crisis reached breaking points where communities had to choose between dying in place or becoming refugees seeking water elsewhere. Economic collapse followed water shortages as agriculture failed. Livestock died, and craftspeople couldn't operate workshops requiring water. This survival pressure created the perfect conditions for engineering innovation. Communities began investing enormous resources in permanent water security systems, understanding that short-term thinking meant long-term death. The water crisis became the catalyst that drove medieval engineering to develop solutions that modern technology still struggles to match. Part 2. The Genius Solutions Roof Networks. Medieval communities transformed every building into a water collection device by creating sophisticated roof network systems that captured rainwater with remarkable efficiency. Cathedral builders pioneered large-scale collection using precisely angled stone roofs that channeled water. Through elaborate gutter systems directly into underground storage chambers, house roofs were modified with specific slopes and materials that maximized water capture. While preventing contamination from bird droppings and debris, clay tiles and slate provided ideal surfaces that cleaned themselves during rain while directing maximum water flow toward collection points. Interconnected gutter networks connected entire neighborhoods, allowing water from multiple buildings to flow into centralized storage systems. The engineering required calculating roof surface areas, rainfall patterns, and optimal positioning to capture water from different wind directions during storms. Master builders developed standardized roof angles and gutter dimensions that became medieval building codes, ensuring every structure contributed to community water security through coordinated collection efforts. Underground cities. Medieval engineers excavated massive underground cistern systems beneath villages that created hidden water cities capable of storing millions of gallons. These weren't simple holes, but sophisticated multi-chamber complexes, with curved ceilings that prevented collapse while maximizing storage capacity. Construction required understanding bedrock geology, water pressure dynamics, and structural engineering that kept chambers stable for centuries. The largest cistern systems featured multiple levels connected by channels that allowed water to flow between chambers while maintaining separate storage areas for different water qualities. Waterproof lining techniques used combinations of clay, lime mortar, and natural sealants that prevented seepage while allowing controlled water movement. Access shafts included pulley systems and stone stairs that allowed community members to retrieve water safely even during winter conditions. Chamber designs incorporated air circulation systems that prevented stagnation while maintaining water quality during extended storage periods. These underground cities represented medieval civil engineering at its most ambitious scale. Gravity. Magic medieval water distribution systems used pure gravity engineering to deliver water throughout villages without any mechanical pumps or external energy sources. The genius lay in understanding elevation differences and hydraulic principles that created consistent water pressure using only natural forces. Engineers positioned storage cisterns at optimal heights that allowed gravity to push water through distribution networks with sufficient pressure for daily household needs. Channel gradients were calculated precisely to maintain steady flow rates without creating erosion or stagnation problems throughout the distribution system. Pressure regulation used strategically placed overflow chambers that prevented system damage. During high-demand periods, while ensuring consistent delivery, distribution networks included multiple pressure zones that allowed water to reach different village elevations while maintaining adequate flow rates. The engineering principles created self-maintaining systems that operated continuously without human intervention, delivering fresh water to individual houses through permanent infrastructure that functioned reliably for generations, using only gravitational force as the power source. Natural filters. Medieval communities developed sophisticated multi-stage filtration systems using natural materials that purified collected rainwater to drinking quality standards. The filtration process began with settling chambers, where sediment and debris separated from water through gravity, settling over extended time periods. Sand filtration layers used specific grain sizes arranged in precise sequences that removed progressively smaller particles while maintaining water flow rates. Charcoal filtering employed activated carbon from specially burned wood that removed chemical contaminants and improved water taste significantly. Gravel beds provided mechanical filtration while creating beneficial bacterial environments that broke down organic pollutants naturally. Multiple filtration stages allowed water to pass through increasingly fine filtering media, ensuring final water quality met safety standards for human consumption. The natural materials were renewable and locally sourced, making filter maintenance economically sustainable for medieval communities. Filtration effectiveness was so advanced that archaeological testing of medieval water systems shows purification levels comparable to modern treatment standards. Overflow control. Medieval engineers created sophisticated overflow management systems that prevented devastating floods. During heavy rainfall, while preserving precious water during normal conditions, emergency spillways automatically diverted excess water away from storage areas when cisterns reached maximum capacity, protecting underground infrastructure from pressure damage. The overflow systems included multiple drainage routes that could handle different storm intensities without overwhelming individual channels or causing erosion problems. Controlled flooding areas were designated to safely absorb excess water during extreme weather events while preventing damage to houses and agricultural areas. Overflow channels incorporated energy dissipation features that reduced water velocity and prevented downstream flooding in neighboring communities. The engineering included early warning systems using float mechanisms that indicated when storage systems approached capacity limits. Seasonal overflow management adapted to different weather patterns, with summer systems designed for sudden storms and winter systems managing gradual snowmelt. These protective systems ensured that water collection efforts didn't create new problems during extreme weather conditions. Hillside catchments. Medieval communities engineered entire hillsides into massive water collection surfaces using terracing and channel systems that captured water across square miles of landscape. Hillside modification involved creating stepped terraces that slowed water runoff while directing flow towards centralized collection points rather than allowing water to escape downstream. Stone retaining walls built across hillsides created controlled water flow patterns that maximized collection efficiency while preventing soil erosion during heavy rainfall. Channel networks carved into hillsides guided water from multiple collection areas toward village storage systems through carefully graded pathways. The engineering required understanding watershed dynamics and seasonal water flow patterns that varied based on weather conditions and ground saturation levels. Different hillside zones were optimized for different collection purposes, with upper areas focusing on initial capture and lower areas concentrating flow toward storage facilities. Rock formations were modified to create natural collection basins that held water temporarily before directing it toward permanent storage systems through controlled release mechanisms. Monastery masters. Medieval monasteries developed the most advanced rainwater harvesting techniques, creating water systems that supported hundreds of residents while maintaining agricultural operations and industrial workshops. Monastic communities had resources for long-term planning and technical experimentation that led to breakthrough innovations in water collection and management. Their systems integrated water needs for drinking, cooking, brewing, agriculture, and craft production into comprehensive management approaches that maximized efficiency across multiple uses. Monastery water systems included redundant storage and distribution networks that ensured water security even during equipment failures or extreme weather conditions. The religious communities maintained detailed records of system performance, seasonal variations, and maintenance requirements that created technical knowledge bases passed between monasteries. Advanced features included heated distribution systems for winter use and specialized storage for different water qualities needed for various monastic activities. Monastery engineering influenced secular community water systems, as monks shared technical knowledge with surrounding villages, spreading advanced techniques throughout medieval Europe. Seasonal banking. Medieval communities developed water banking systems that stored abundant seasonal rainfall for use during dry months, creating year-round water security through careful resource management. The banking approach required calculating annual water needs against seasonal collection patterns to determine optimal storage capacities for different community sizes. Storage systems included multiple chambers that preserved water quality during extended storage periods while preventing contamination and evaporation losses. Seasonal rotation systems moved stored water through different chambers to maintain freshness while ensuring older stores were used before spoilage occurred. Water banking included rationing protocols that managed consumption during dry periods while ensuring adequate reserves for emergencies and extended droughts. The banking systems incorporated weather prediction knowledge that helped communities prepare for seasonal variations in rainfall patterns. Advanced banking operations included trading relationships with neighboring communities that allowed water sharing during regional drought conditions. These seasonal banking systems represented sophisticated resource management that ensured consistent water availability regardless of weather patterns. Community coordination. Medieval water systems required unprecedented community cooperation and coordination that created sophisticated management structures governing every aspect of water collection and distribution. Village councils developed detailed regulations controlling individual water usage, maintenance responsibilities, and resource sharing that ensured system sustainability. Community labor was organized into specialized teams responsible for different aspects of system operation, including collection, storage, distribution, and maintenance activities. Water rights systems established fair access protocols that prevented conflicts, while ensuring adequate supplies for all community members during normal and emergency conditions. Coordination included seasonal work schedules that aligned maintenance activities with weather patterns and community labor availability throughout the year. Educational systems trained community members in proper system operation and emergency procedures that maintained water security during crisis situations. Intercommunity coordination created regional water management networks that shared resources and technical knowledge between neighboring villages. These coordination systems represented early examples of sophisticated resource management that required complex social organization and cooperative planning. Water quality control. Medieval communities developed sophisticated water quality testing and maintenance systems that ensured collected rainwater remained safe for human consumption throughout extended storage periods. Quality control began with visual inspection techniques that identified contamination signs, including color changes, sediment accumulation, and surface film development that indicated bacterial growth or chemical pollution. Taste testing protocols used trained community members who could detect subtle flavor changes that signaled water quality problems before they became dangerous. Storage rotation systems moved water through different chambers to prevent stagnation, while ensuring older water was consumed before freshness deteriorated. Cleaning schedules included regular cistern maintenance that removed accumulated debris and biological growth that could contaminate entire storage systems. Village transformation successful rainwater harvesting systems completely transformed medieval village life by providing water security that enabled population growth, economic development, and cultural advancement. Communities with reliable water systems could support larger populations, develop craft industries requiring water, and invest resources in activities beyond basic survival needs. Agricultural productivity increased dramatically as guaranteed water supplies allowed expanded crop cultivation and livestock operations that weren't dependent on natural rainfall patterns. Economic development flourished as craftspeople could establish workshops requiring water for metalworking, brewing, dyeing, and other specialized trades that created village prosperity. Water security enabled communities to weather crisis periods that devastated neighboring settlements, making successful villages attractive destinations for refugees and new residents. Cultural development advanced as communities freed from constant water anxiety could invest time and resources in education, religious activities, and artistic pursuits that enhanced quality of life. Population stability created generational knowledge transfer that allowed technical improvements in community development over extended time periods. Successful water systems became foundations for medieval urban development that supported thousands of residents through sophisticated infrastructure planning. Modern lessons medieval rainwater harvesting principles offer crucial insights for modern water security challenges as cities worldwide face increasing drought conditions and infrastructure failures. The decentralized approach that made every building a water collector provides alternatives to centralized systems, vulnerable to single-point failures during emergencies. Gravity-based distribution systems offer resilient alternatives to electrical pump systems that fail during power outages and natural disasters. Natural filtration techniques using local materials provide sustainable water treatment options that don't require expensive technology or chemical inputs. Community coordination models demonstrate how local management can create more responsive and sustainable water systems than distant bureaucratic administration. Underground storage systems show how communities can build long-term water security using local labor and materials rather than depending on complex supply chains. The integration of water collection with existing architecture provides models for retrofitting modern buildings with rainwater harvesting capabilities. Seasonal banking approaches offer frameworks for managing water resources across irregular weather patterns that are becoming more common due to climate change. Medieval water wisdom provides tested solutions for modern communities seeking water, independence, and security. Subscribe for more medieval engineering secrets that could revolutionize your water independence today.